Okay, allow me to share my screen. So for this afternoon, we're going to discuss higher order differential equations. And we're going to start with distinguishing the classification of higher order differential equations. So we classify them either as homogeneous or non-homogeneous higher order differential equations. Now you can see in here two differential equations. So this one is second order. The highest order derivative is 2, and this one is fourth order. Okay, so both are higher order differential equations. This one is a third order differential equation. This one is also a third order differential equation, but different than this one in the sense that in here, in this particular example, you could see that your unknown function y is raised to 2. So while this one is higher order and linear, this one is higher order but non-linear because of the exponent 2 of the unknown function y. But both are higher order DEs. Now this one is also third order, and this is also linear. So the difference of this one and this one are in the coefficients of the derivatives of the unknown function. So you can see in here that your y prime has a coefficient of -1, while in here your y prime has the coefficient of -e raised to x. The rest of the coefficients are the same. So they are said to be homogeneous and linear higher order differential equations. So if we have the concept of homogeneous in first order DE, you also have the concept of homogeneous and non-homogeneous higher order differential equations. We'll go to the specific distinguishing fact about the two, the homogeneous and non-homogeneous differential equation in the next slide. Now this one is also third order. This is non-linear. Okay, based on what we have studied, this is non-linear because of this. Your y prime is multiplied to the unknown function itself. So a DE is said to be nonlinear when the derivative of the unknown function is multiplied to the unknown function itself. Okay, so this is third order nonlinear. This is third order also nonlinear. This is third order. This is third order linear. This is second order. And this is fourth order. This is also linear. Okay? Now, examples. These are examples of higher order differential equations. So now let's go to distinguishing homogeneous and non-homogeneous differential equations. What you see in here are two general formats of how we write a differential equation. The y here raised to an exponent which has a parenthesis is the derivative of your unknown function, because your exponent here is enclosed in a parenthesis. So whenever an exponent of a variable is enclosed in a parenthesis, it denotes that is the derivative of your variable, not that it's the exponent of that said variable. So this is the nth derivative of y. This is the n minus 1 derivative of y. So if this is y raised to 5 with n equal to 5, so this must be 4. And then you have here the last two terms in the format. You have y prime, and then the last term is y. If you notice, all the coefficients of the derivatives of the unknown function and the unknown function itself, which is y, are functions of x. Okay, they are functions of x. And the right side of this expression that are added, so it could even be subtraction, but generally we write it as plus, is 0. Now, here comes the other format below, exactly the same as what we have here on top in terms of what is written on the left side. So exactly the same on what is written on the left side. However, the right side of this is a function of x or a g of x. So then you may think that one must be homogeneous and the other one must be non-homogeneous higher order differential equations. So let's see. So the one in which the g of x or the function of x on the right side is 0 is said to be a higher order homogeneous differential equation. The one in which the right side is a function of the independent variable is the non-homogeneous differential equation. So this is how we write the format of a homogeneous and a non-homogeneous higher order differential equations in which the coefficients of your variables are all functions of the independent variable. Now, some of the terms in here, because the terms are arranged in which your derivative of a known function starts with the highest order down to the least, it could be that some of the derivatives in this arrangement could be missing. But as long as the format conforms to this, then your said higher order DE is said to be either homogeneous or non-homogeneous. So these are specific examples below. So you could see here 3y triple prime plus 5xy double prime minus e raised to xy prime plus 7y minus cosine of x equal to 0. And the second example is 3y triple prime plus 5y double prime minus e raised to xy prime plus 7y equal to 0. Now, can you please write on the chat box which of the two equations or write down the number of the equation which is said to be homogeneous. Please write on the chat box. We'll see who will get it right. So write the number of the equation, higher order differential equation, which is homogeneous. Okay, I have one answer. Carlos, Kyle, John Mark. What about the rest? Janessa. Everesto Cassie. It's so easy actually to tell which is homogeneous and which is non-homogeneous. So all the answers that were sent to the chat box are correct. So in terms of, there is one in here which is a different answer. So nonetheless, this will be the correct answers for the two. Number 2 is homogeneous, whereas number 1 is non-homogeneous. It was made to look homogeneous by setting the right side equal to 0. Okay, the right side was written as 0, but actually it's non-homogeneous because the last term here on the left side should be either the lowest order derivative or in terms of the unknown function. So this should be the last term here on the left side. The cosine of x should have been written on the right side. So you were dissuaded to think that this is homogeneous, but actually it's non-homogeneous. Okay, so you have to make sure that the format on the left side, again, is comparable to the general format that is written here. So the last term on the left should be in terms of the unknown function or the lowest order derivative in your given differential equation. Okay, so I hope that made things clear now as to how to distinguish higher order homogeneous differential equations from non-homogeneous higher order differential equations. We don't do any testing here. We just simply compare the form of the given DE to the general format of a homogeneous or non-homogeneous higher order DE. Now, in the examples in here, you have to choose the letters that will coincide to the particular characteristic or definition of such particular differential equation or the type of differential equation. Okay, so I'll click one here. You could see that if you are asked which of the examples on the left are second order DE, what do you think is the answer? Which of the DE on the left side, A, B, C, D, E, is a second order DE. You may write your answer on the chat box again. Which of the DE written on the left side is a second order DE? Okay, I only got one answer. What about the others? Okay, I have 2. I have 3. What about the others? I only have 3 answers here. There's 9 of you in this class. It's so easy to tell which of the following differential equations on the left is a second order DE. Another one, give me another answer. Okay, sige. So I have 4, I have 5. Sige. So the following got it right. So we have Janmar, Janessa, and Kyle. Okay. All of the differential equations you're seeing here are said to be second order. So all. Okay, what about it's second order and it's linear? Okay. So the coefficients of your unknown function and the unknown function itself should be functions of the independent variable only. So which of the differential equations you have on the left is linear and second order? Only have 1, 2. Okay, Janessa, Carlos, Kyle. Okay, so second order linear differential equations are the following. So you have letter A, letter C, letter D, and letter E. Okay, they are all second order and linear. What about this? Second order, homogeneous, and linear. So this is the format actually that is written for that particular type of DE. This is the format for a second order homogeneous and linear DE. Which of the following is under this particular distinction or category? Second order, homogeneous, and linear. Okay, Carlos, Dinesa, Kyle, the same people that have been answering me correctly. Carlos, John, Mark, Dinesa, Kyle. Correct. Some answered also correctly, but there are some answers that are missing. Okay, so the answer is letters D and E. D and E. The right side should be 0. It has to be linear and it has to be second order. Okay, now next. Second order, homogeneous, linear, with constant coefficients. So you see here, A, B, and C should be constants. So which of the following is under this category? It has constant coefficients, it is linear, and it is homogeneous. Okay. So I have Lopez, Carlos, Quinto, Labto, Kyle, all of which have correct answers. The answer is just letter D. It's the only homogeneous linear higher order differential equation, specifically second order, which has constant coefficients. So the coefficients of your derivatives here and your unknown function itself is 4, -3, and 1. Okay, so that's it. So you know now how to distinguish a particular differential equation based on the formats that were shared in here and based on the examples in which you are to pick those that falls on a particular category. Now, we go to homogeneous linear differential equations with constant coefficients. So this is what we're going to learn this afternoon. How do we evaluate? How do we find the solution of a homogeneous higher order linear differential equation with constant coefficients? So the format is something like this if it is said to be homogeneous only. But if it has to be with constant coefficients, then we have to, in this case, we have to do away with the x. So this should be only constants, okay? No functions of x for the coefficient of the unknown function and its derivatives. Now, this one is a homogeneous second order, higher order differential equation which is linear and which has constant coefficients. Now, this one is also another example. Now, you see that there are two possible roots for this particular equation. And when we write its solution, we need to consider all this particular exponential function as its solution. So the question is how? How did you get that y1 of x is e raised to 2x and y2 of x is equal e raised to 3x? That will bring about the solution to this particular differential equation. Anybody who can guess what was the basis that was used in finding y sub 1 of x and y sub 2 of x? Anyone here who has an idea? What was the basis used in determining these expressions? Nobody has an idea. So, okay, let me proceed to the next slide so you will know how it was solved. So, how to solve? If you're given this form of your homogeneous higher order differential equations with constant coefficients, because you see here that P sub 1, P sub 2, P sub n, including P sub 0 should be constants, not equal to 0. So they should be constants not equal to 0 or some of which can be 0. But it is a requirement that this P sub O, the starting coefficient of your highest order derivative, should not be equal to 0. They should be constants. Number 2, you are to write the derivative of your unknown function as capital letter D. The D of dx. So your unknown function is y. So that is why we write it as dy dx. So if it's just a general representation of the derivative of any unknown function for that matter, we simply write it as d. We refer to that as the operator d. Okay, one second to the last method is the method of the operator d. So you're going to change all the derivatives here and represent it in the shortcut manner like this one. So that the nth derivative of y with respect to x is written now as d raised to n y. Okay, let me annotate. This one, the d raised to n y represent the nth derivative of y with respect to x. Why? Because the d represents the d of your unknown function with respect to x, and we call that as the operator. So you change all the d's here, or rather derivatives here, to this d. Okay, you have done that in here. Of course, the last term, which is your unknown function, does not have the d because it's just your unknown function and the constant p sub n. So still the right side is 0 because we're talking of the solution of a homogeneous higher order DE. Now you can write it even in this manner here, simplified, where all the y's or all your unknown function is factored out in here. So you have p sub o d raised to n plus p sub 1 d raised to n minus 1 and so on until you have the last term, which is p sub n. So now this expression is written in textbooks and reference materials as the f of d. This one, the f of d without the y. So they are f of d written as f of d because they represent the function of the operator d, where the operator is the representation of the derivative of your unknown function. Okay, so that's just how we write it, the manner of writing it. But the next part here is very important. The function of d of y is equated to 0. And this f of m without the y, we change the d to m, or the function of the d is equated to 0. This equation is known as the characteristic equation. You simply change the d to small letter m. You get rid of the y. Now, the purpose is for you to get the roots of this function of m. So the roots of the characteristic equation of your function of m coming from the function of d are called your characteristic roots. So the nature of the roots determine the form of the general solution. So if the roots are real, you will have a different form for your general solution. If it's imaginary, it's a different form. If it's complex, it's a different form, and so on and so forth. So to go back to the previous slide, which says how did we get these two? We simply factored out this particular, the characteristic equation coming from this particular differential equation. So what do I mean? I can rewrite, so let me annotate. I can rewrite the second order derivative as d2 5d, and I have 6, then I'll place here y, and it's equated to 0. This is comparable to the f of dy equal to 0. You just simply get rid of the y and change the d's here to m. So what do you mean? So that would mean like m squared minus 5m plus 6 is equal to 0. This expression now is the f of m, which was equated to 0. This is the expression you saw in the slide that we discussed a few minutes ago. So what is the purpose of this characteristic equation? It will point out to you the roots. So this is where your algebra comes in. You simply find the roots of this equation. So from algebra, by factoring, the roots would be m minus 3 and m minus 2. This would be 6, and the middle term will be negative 5. So with this now, you will have m equal to 3 and 2, right? Now you see this? You see the arguments of the exponential functions, they were based on these roots of your characteristic equation. So if you have real roots, the terms that appear in the general solution of your higher order homogeneous DE will be exponential functions in which the exponent are the characteristic roots, which are said to be real. So if you write down the solution of this particular homogeneous higher order DE, it is written as y equal to, we introduce the arbitrary constant c, so we write c sub 1 e raised to 2x plus c sub 2 e raised to 3x. Can we interchange these two? The answer is yes. Can we change the c sub 1 and c sub 2 to any letter? The answer is yes, as long as these two exponential functions appear in the solution. So very easy. This is already the solution of this second order homogeneous differential equation with constant coefficients. Now, any questions before I go to the next slides? Okay, so I have here in the chat box. It's okay. Noted. No questions here? Sige. So we'll now continue because there are examples here. So this would be now the different roots that you will be getting if you process a higher order homogeneous linear differential equation with constant coefficients. So the first step is you write your DE in this form. Second is you write the characteristic equation, the f of m. And third, you find the roots. If the roots are distinct and real, so what do we mean by distinct? You know what is real, of course. I know real number. Distinct is they're not the same. So they are unique from each other. So your terms in your general solution will constitute of exponential functions. Okay? Where the arguments are the distinct real roots. In this case, it's represented in here as m sub 1 and m sub 2 because in the general format that is being shown to you in here, you have a second order homogeneous differential equation. If it's second order, you are expected to have 2 roots. If it's third order, you will have 3 roots, and so on and so forth. So the order of your DE tells how many roots there are to find for your given homogeneous or non-homogeneous higher order DE. So if the roots are repeated, so meaning your M1 and M2 are the same, that is why it's called repeated. So the same sila. So your other root should be altered or made unique from the other by multiplying it by the independent variable. So since M1 and M2 are equal, instead of just writing like this, because they are being repeated, you will multiply the next exponential function by x. For example, you have another one. Let's say it's an M3 because in here, this is just an example, you have a third order DE. Then you will alter the third root by not multiplying only by x but by x squared. So the goal is you will make all the terms in your general solution to be unique. They should not look the same. Okay? But that's in the case if this is a third order DE that will yield 3 roots. What about if the roots are imaginary? Imaginary roots result from roots which are negative, like square root of 25, square root of negative 9. So the root of this is plus minus 3i. This one is plus minus 5i. It's said to be imaginary. So if the roots are imaginary, you will not anymore use the exponential function, but you will use the pair of the cosine and the sine. Okay? If you have this plus minus 5i as your imaginary root, for example, your general solution for this would be c sub 1 cosine of 5x plus c sub 2 sine of 5x. That's it. So can you interchange these two? Of course, yes. The sine could come first, followed by the cosine. But the argument of your sine and cosine function is the magnitude of your imaginary root. So it's 5. So if it's 3 in here, then this should also be 3. What about if it's a complex root? Okay, complex roots or complex numbers, you're done with your algebra, are numbers which has imaginary and real parts. So example of a complex root is plus, or rather 1 plus minus I. So if this is interpreted, you have one root which is 1 plus I, and the other root is 1 minus I. Right? So they always come in complex conjugate pairs. Complex pair. Conjugate in the sense that one is the negative of the other. In terms of the imaginary part. So if you have already complex roots, you will now use both the exponential and the sine function. The exponential function, which is being multiplied to the cosine and the sine, will follow the value of the real part, or will have its argument representing the real part of your complex root. So if this is 1, in this case 1, so this should be 1. This should be 1. In the case of this one, since it's plus minus I, the argument of the cosine and the sine function would also be 1, or should also be 1 because it's in here 1. So this should be cosine of x and sine of x. It's understood to be that the coefficient of the x is 1. Okay? So these are the 4 different scenarios that you will be getting when you determine the roots of your characteristic equation. So some characteristic equation have orders higher than 3 or 4. So some may have a combination of any of this that you are seeing. But nonetheless, each of the roots have their own unique way of representing such a root in the term of the general solution of your DE. Okay? Now, I will clear my markings here and we go to the next slide. So if the roots are real and distinct, like this one, this is your characteristic equation. We just change the D to M. This is our first example. These are your real unique roots. So this would be the 2 terms that will appear in your general solution. And another one is this. So you have that one, second order. So m squared minus 4. So if you transfer the 4 in here, you'll be getting the square root of 4. So square root of a number is either plus minus 2. So still unique and distinct. Okay, so the general solution of these two, for the first one, you will have this and this being added. And for the second one, you have this and this being added. You can interchange the manner of writing. Any question? None. Okay. Then we'll go to real repeated roots. Okay, they are real, but they are repeated. So this one. Okay, your characteristic equation is this. If you do factoring, you will have the same roots. So it's m minus 2 quantity squared actually from your algebra. So you have to modify one of your roots. Okay? Okay, another one of this. This is a third order derivative. So we expect 3 roots. This one is second order, so we expect 2. So if you write the characteristic equation, it would be something like this. If you do your algebra, your roots will be 0, 2, and 2. You factor out m first, and it would be multiplied to an expression like this on the first example. So what will happen now? You will have e raised to 0x for the 0, that's 1. And for this 2, you will have e raised to 2x for this one. For the second one, you need to modify. Okay, because it has been repeated. So the final answer for the first one is this. It's always suggested, class, that you write in the first term the root or roots that were altered. Okay, then in here. So you have that one, then you have this. And since your third expression is just a constant, so you represent it simply as a constant, which is C sub 3. Any questions? Okay, then we'll proceed if there are no questions. What about this? So fourth order derivative. This is your characteristic equation. If you factor out, you have this. So your root 1 is repeated not just twice, but thrice. So how will you write its solution? So you have 1 for the e raised to 0. You have e raised to x for 1. You have x e raised to x for the second one, and x squared e raised to x for the third one. And this should be your general solution. You can also write it like this one first, followed by this, and the last is the constant. Question? Okay. Then we go to imaginary and repeated imaginary roots. Okay. What if it's imaginary and repeated imaginary roots? So you'll have this example. This one. The characteristic equation is this. So if you transfer 4 on the right side, it will become -4, right? The -4, if you take the square root of that, will be a plus minus 2i. Plus minus 2i. Okay, you have that. So in here, we have to get the cosine and the sine function to represent that 2i and the minus 2i. So you have it in here, the 2, in the argument of the sine and the cosine. Now, what about here? You have y to the 4th, 8y raised to 2 plus 16y equal to 0. Actually, this is y, the 4th derivative of y, not y to the 4th. I read it very wrong. Okay, so if you write the characteristic equation, this is m to the 4th. Okay, if I will annotate, this is actually m to the 4th plus 8m squared plus 16 equal to 0. So this one, if factored, would be this. Okay? So if you take 1, m squared plus 4, just like this, amo na siya. Ang imo pair of imaginary roots. And it's being repeated because this one is squared. So in that case, I will now clear my markings. You will have something like this. A plus minus 2i for the first m squared plus 4 and a plus minus 2i for the second. Because you see this, it's 2. So what will you do? You have a case of a repeated imaginary root. If this is the first pair, the second pair should be altered, made unique by multiplying it with the independent variable, just like the way we do it with repeated real roots. So you have this one, the first pair, and you have this one for the second pair. Just like the way you have altered the real repeated roots. So the first one will have this as the general solution. The second example will have this as the general solution. You can write these first two in here and then followed by this one. Doesn't matter as long as all these 4 roots, root representations are present. Okay, any questions? Okay, then we proceed. What about complex roots? This is the last type. So you have here a second order DE. This is your characteristic equation. And since it's a second order equation in algebra, or a second degree equation, you may use the quadratic equation. Okay? If you use your quadratic equation, these are your characteristic roots. Negative plus 2i, negative 1 plus 2i rather, and negative 1 minus 2i. So your representation for the answer would be the e raised to mx, where m is the constant, the real number constant in your complex root. And the 2i here is the argument of the cosine and the sine. So you can see here you have e raised to minus x for the negative 1 times the quantity c sub 1 cosine of 2x for the 2 in the imaginary part plus sine of 2x. So this is how we represent the general solution of a differential equation which has a characteristic root in the form of a pair of conjugate complex roots. Okay, complex siya. So ang real part is represented by the exponential function. The imaginary part is represented by the pair of the cosine and the sine function. So they are multiplied. Okay, it's not added, but it's multiplied. Any questions? Sige, we'll proceed. So the next part, still on complex roots, is this. You have a third order DE. This is your characteristic equation. If you're going to do factoring, you will have m minus 1 and you have this. You can use synthetic division in here, or you can simply use your calculator in finding the roots. But for the second part, you need to use quadratic equation because this is a quadratic equation. So your roots are your M1 rather is not 0 class, but rather it's 1. You see here, it's 1. It's a mistype. I just checked. I'll just correct this one. This should be a 1. Okay? And then you have this pair of complex conjugate roots. The real part is negative 1/2. You could see here you have e raised to negative x over 2 for the negative 1/2. For the imaginary part, you have the square root of 3 over 2. So you have to use the cosine and the sine. And for the root, which is 1, in the case of m minus 1, you have c sub 1 e raised to x. So your arbitrary constant for the pair of complex conjugate root representation is the one that is being multiplied to the pair of cosine and sine. Or yes, to the set of function sine and cosine. So don't forget this exponential part here, which accounts for the real part of your complex conjugate root. Now, your square root of 3 over 2, same thing in here, is in here. Is for that one. Any questions? Okay, I think there's none, so we will proceed. Okay, that's the end of our topic for today. I'll stop sharing. Do you have any questions, class? For Thursday, we'll be discussing solutions of or different ways or techniques in finding the solution of non-homogeneous higher order DE. I think on Wednesday, we'll be discussing the use of the method of undetermined coefficients. There are 4 techniques that could be used in evaluating non-homogeneous higher order DE. So it's easy if it's homogeneous, but if it's non-homogeneous, it's still actually procedural, easy, but it will take time because some solutions are quite lengthy. Do you have any questions?